All right, so we've been talking about, I think it's chapter 21, I want to say. We've been talking about transition metals last time. So again, for the transition metals sort of aspect of it, some of it might have been some review for you. Um, you do need to obviously know, like we talked about last time, about transition metals, some of their properties. We talked about electron configuration. We also talked about some general trends that you find on the periodic table. Um, we talk about ionization energy, sort of what it is, electron affinity, those type of things. So those general sort of trends, and again, a lot of those things probably you're familiar with to begin with, and obviously about electron configuration of transition metals with and without charges, are sort of things that you need to know. Now we sort of reviewed the transition metals because we're going to kind of now talk about really complex ions, and a lot of complex ions do contain sort of transition metals sort of in the center of them. As we'll talk about, a complex ion really is a metal that has a number of ligands sort of attached to it. Um, So those sort of transition metals do share some properties with our complex ions that we're going to be talking about at this point. So why don't we get started on that? So first off, we're going to talk about coordination compounds, and really a coordination compound, you could kind of think of it almost like an ionic compound. And the idea behind that is a couple of things. A coordination compound consists of really two things. It consists of a complex ion, and it consists of a counter ion. So much like when you think about an ionic compound, just a run of the mill sort of ionic compound, we have kind of a positive guy, right? We got like a cation, got that positive cation, and we have that negative anion. And a coordination compound is very similar in that aspect. There's a positive part and a negative part. And it really does sort of depend on the situation as to, which one's positive, which one's negative. And what I mean by that is, since a coordination compound is made up of a complex ion and is made up of a counter ion, we could actually have really kind of two different combinations that can occur. Our complex ion could be positively charged, which would mean that our counter ion, really just to balance out the charge, would be negatively charged. Vice versa, we could also have a complex ion that's negatively charged, and that would mean that our counter ion would be positively charged. So it is possible, as we will see, that both the complex ion could be either a positive overall ion, could also be a negative overall ion. And that would mean that obviously your counter ion, which is much like the name implies, they're really just to balance out the charge in this sort of compound, could either be positive or negative. Also, like an ionic compound, when we deal with sort of coordination compounds as well, we sort of do our positive guy, then our negative guy. So always sort of cation first and then anion in terms of sort of names and kind of formulas and those type of things as well. So let's talk a little bit about, again, a complex ion. A complex ion really contains a central metal cation. A lot of times it can be a transition metal. It's a lot of times a small metal with sort of a large positive type charge, like +2, +3, that type of situation. We come across some of these complex ions a little bit earlier when we were talking about salts, and remember, something like aluminum that's basically surrounded by a bunch of waters can act as an acidic salt, and it really is sort of a complex ion of aluminum and water together. um, these are metals that have one or more sort of molecules or ions bound to them. Those molecules or ions are what are known as ligands. So our guy in the middle here is our metal, and again, everything attached is our ligands here. So in this case, the chlorine, the ammonia here, and those are all the ligands that are attached in this case. What are ligands? Well, ligands, as we've talked a little bit about in an earlier chapter, I believe, but ligands are essentially Lewis bases. And if you remember what Lewis bases are, right? Lewis bases are guys that will, donate a pair of electrons, right? So they're going to donate those pairs of electrons. And what makes something a good Lewis base is things that are negatively charged, things that are negatively charged, things that are polar and have some non-bonding electrons. So if you think about these guys here, what really is the Cl here? It really is Cl minus, which means it's gained some electrons. So it's got those electrons to give. NH3 is a polar molecule. And also has those non-bonding electron pairs to sort of donate. So a ligand, which is again a Lewis base, what makes sort of really good ligands, as I just drew there, and we see on the bottom, is really things that have negatively charges because they have sort of, if you want to think about it, an excess amount of electrons happening, which means they do have electrons to donate. And things that are kind of polar with some non-bonding electrons around them make some really good Lewis bases as well, or ligands. And that's what we see here with water. Water, again, polar, right? Heading in that direction. We got those non-bonding electron pairs, and that's why, it's a fairly good ligand as well. Any questions on that there? So another important thing when we talk about sort of ligands and how many of these sort of molecules are attached to the metal in a complex ion is the idea of coordination number. And coordination number basically describes how many atoms are directly bound to the metal in the complex ion. So when we talk about the coordination number, is not necessarily always just like the number you see in the formula. And what I mean by that is, sometimes people will have a formula for a complex ion, for example, where they have like a metal and, they got Cl4 and, the coordination number here would be 4. But, you could have a metal that has something else involved, like this guy. And you may look at it and go, oh, well, then obviously the coordination number is 2 because, hey, there's 2 of these. So that makes sense because there's 4 here. So there's 4 of these guys. So that would make sense. But in reality, there's actually different types of ligands that attach. There's different types of here. And what I mean by different types is there are certain ligands that have the ability to attach to that metal in, say, just one location or one atom per ligand. And that would be ones that are sometimes referred to as being monodentate, mono meaning one, sometimes referred to as unidentate as well. Monodentate, things like water, where water attaches through the oxygen, ammonia attaches through the nitrogen, and obviously chlorine, since it's the only guy there, attaches through the chlorine as well. So in the case of where we have a metal and we look at the formula and the ligand is just Cl and there's 4 of them, the coordination number here would be 4 because that's basically how many atoms are attached to it. There's 4 Cl's basically attached to the metal. But there are also some ligands that attach in, say, 2 places per every molecule. And those are sometimes referred to as bidentate. Bidentate obviously means 2. Ethylenedyldiamine, which is abbreviated with the EN, like I wrote right here, which is this guy. And if we were to do like a little drawing of that guy, give it the old college try here. Let's see what we got here. I'll do a little bit of that move. Do a little bit of this move. And maybe a couple hydrogens on those guys. So this is actually the structure of ethylenedyldiamine, are very, very often abbreviated as just EN. And what happens when a metal is there and this ligand comes into play is it will attach per molecule through this nitrogen because it's got that lone pair, but it will also attach through this nitrogen, which also has that lone pair. So for every molecule of ethylenedyldiamine, you're getting like a 2-for-1 deal. You're getting basically 2 attachment points. And coming back to my example here, if I had 2 of those molecules, it would also attach to this nitrogen, and it would attach to this nitrogen. And if we now count up what the definition of coordination number is how many atoms directly attach. That is 1, that is 2, that is 3, and that is 4. So the coordination number here actually for this one, even though the little subscript is a 2, coordination number here would actually be 4 in this particular case. Questions on that there? So it's important to be able to identify some of these ligands, some common ligands, and remember that they don't always, in every case, attach basically 1 atom per molecule. Some, like we see here with ethylenedyldiamine, has the ability to attach in 2 places. Another bidentate, which is a common one, is C2O42-. That's our good friends Oxalate. And if you draw oxalate, it looks something like this. Again, give it the old college try here. Yeah, it looks something like that. And a little bit like that. And -1 on that guy, -1 on that guy, kind of where the formal charge is. So again, in this situation, if oxalate was to sort of hook up with a metal, this oxygen here would bind, and in the same molecule, this oxygen here would bind. Again, giving you a 2-for-1 situation here for every oxalate molecule that basically attaches. Any questions on that there? Now, in addition to monodentate, which they bind 1 per molecule, bidentate, which they bind 2 per molecule, there are some that bind in more than that. So there's some that are just classified sometimes as polydentate. Polydentate means that they attach in multiple places, 3 or more atoms. EDTA, ethyl diacetic acid, tetraacetic acid there, binds in 6 places per every 1 molecule. So this guy does a 6-for-1 situation. So there's a number of different ligands that can bind in multiple places. Any questions on ligands here? We'll see a table here in just a second of some different ligands and sort of how they bind, so you can have an idea of which ones are commonly seen. Now, the other kind of question is, how do we know, in a situation, how many ligands might attach to a particular metal? Although it does vary, there is sort of a common sort of number of ligands that will attach per sort of metal, if you will. And a lot of it is sort of based on charge. So if we look over here, here's some common transition metals that have +1 charges, right? And you can see for a vast majority of our +1s, it's going to be a coordination number 2. A couple of them can do 4 as well. So it is sort of situational, but 2, 4. We do see that as our charge sort of increases to like a +2 for some of these transition metals, common ones are 4s and 6s in terms of coordination numbers. And obviously, as you can see, as the charge gets even larger here to +3, common is 6, except for gold. Gold kind of rolls with 4 in the gold 3 aspect of it in the middle there. So sort of the larger the positive charge, not a perfectly great trend, if you will, but you can kind of fit more ligands in. If you just think about it, greater the positive charge means that it is much more electron deficient, right? And in this case, if our ligands are acting as our Lewis bases, that means that probably our metal is acting as like a Lewis acid. And a Lewis acid is something that will accept a pair of electrons, which means it's basically electron deficient. The higher the positive charge, the more electron deficient it is, the more ability it wants to probably pick up some electrons. And that's why we could kind of get more sort of ligands attached in that particular case. Any questions on that there? All right, so here's just some of those pictures of our ligands. Looks like I drew it all right, not bad. This is EDTA, this big molecule on the right. And again, you can see in something like EDTA, it's a very, very good sort of grabber of metals, if you will. It's like binds there, 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 and there. Those basically are 6 spots where our coordination number of 6 basically comes from in terms of how that binds. Over here is 3 molecules of ethylenedyldiamine, or that EN. And again, each molecule here binding twice, this molecule also binding twice, and this guy binding twice. So again, if you saw a formula for this guy, it would look something like, you know, the metal and EN3. Again, that 3 not going to give you the right coordination number in this sort of compound here. 2, 3, 4, 5, and 6 would be the coordination number for this compound. And obviously 6 would be the coordination number for this compound. So sometimes ligands are what are referred to are bidentate ligands or polydentate ligands. They're sometimes referred to as chelating agents. Chelating agents are essentially guys that basically grab around metals and sort of tie them up. So, you know, you sometimes will, even if you look at labels on things, you know, like shampoo, other things like that as well, you'll see in the sort of labels sometimes of ingredients, you'll see something and it'll say like EDTA. And, you know, again, it's a very good sort of metal grabber. It basically surrounds the metal and stuff like that in a very efficient manner. Obviously for EDTA, 6 sort of places where it grabs that metal per every molecule. Here's a table, again, similar to one you should have in your book, I think, of some of these different ligands. So again, our unidentate or monodentate ligands, each of these guys, again, binding in one place per molecule that's coming in. That's our halides or halogens, basically with negative charges. All these guys here are hydroxide or cyanide or water or ammonia are very common, or nitrite, also a common sort of monodentate ligand. These again are a couple of really common bidentate ligands. That's our oxalate and our ethylenedyldiamine. As I mentioned before, it is common, as weird as it may sound, again, to use that EN not only in formulas, but also in names as well. So a lot of times people don't want to draw out the formula for ethylenedyldiamine or sort of draw out the or write out the name. So it's very common if people use that EN sort of abbreviation in both places. So don't be surprised if you kind of see it pop up along the way. But each of these guys, as we just talked about, basically would bind in 2 locations per every molecule. These polydentates, again, can do 3 or more. Here's an example of a 3. This is diene, is sort of the abbreviation of it. And it's diethylenedyltriamine. Triamine means there's basically 3 of those NH groups. So here's 1, 2, and 3 of those group, which is really where the triamine comes into play. But at each of those nitrogens, again, it has that lone pair of electrons, and it's able to sort of donate those. And it gives it an attachment point there for that ligand to attach to the metal. So again, in this guy, for every one of these guys, you're getting a 3 for 1 situation happening. Here's our ethylenedyldiamine tetraacetic acid or acetate. And again, as we highlighted in the other slide there, you get like 6 per this guy. Again, also in case you're looking at charge, that's on like a -1, a -1, -1, -1. So this overall thing has kind of like a -4 type of charge that's happening there with the EDTA. Again, you should be kind of familiar with some of these definitely ligands. They do come up a lot. And again, not even familiar with sort of what they are, but you know how many times they bind, as that can help you obviously identify the proper coordination number and things like that. All right, so why don't we take a second here and what is the oxidation number of the metal in each of these? And by the way, when we look at something, just to give you some reference point, a lot of times when we do sort of coordination compounds, we oftentimes will put the complex ion in these sort of brackets. So we're looking for really the transition metal. What is the oxidation number on that? So take a moment and see what you come up with. Okay, so let's take a look at this. As I mentioned just a second ago, our complex ion, a lot of times when formulas are written, are kind of put in these brackets. That means typically anything outside the bracket, either in behind or in front, or our counter ion. So let's take a look first off at this guy here. So we have KAuOH4. All right, so our complex ion is here. By default, this would make this the counter ion in this case. So looking at this, we're interested really in what is the sort of oxidation number of the gold in this case. So if we just sort of add up things, OH is OH minus, so that is -1. There are 4 of them, which kind of gives you a -4 overall. On the outside, this potassium is like normal potassium. It is +1 in this case. That means that if we add this up, there's no charge for our coordination compound, and that's the idea of it because we have a counter ion present. So the gold in this case should be +3 in this case. Any questions on that one there? Now let's look at this a little closer and sort of see what does this mean for our complex ion part. Well, what it means for our complex ion part is if we just take the complex ion part, which is this part of it, and we know this guy is -1. Our gold we just determined is +3. Again, using the same logic here, there's 4 hydroxides, gives us a -4. What that tells us is overall in terms of charge, our overall charge here on our complex ion part is -1. And that's important because what we see here in terms of our counter ion is we actually only have 1 potassium. And we only have 1 potassium because it is +1. So ultimately, like an ionic compound, +1 and -1, when we put these guys together, we end up with overall no charge on our coordination compound. So in this particular case, the complex ion is actually negative and the counter ion here is actually positive. Any questions on that there? We also could determine that just simply by the placement of each of those things, by seeing the brackets here, where our complex ion part is, coming second in the formula, we know automatically that our complex ion is actually going to be negative because a coordination compound is just like an ionic compound, positive guy first, followed by the negative guy. So by the positioning in the actual formula of that complex ion, again, without even actually doing the calculation, we know overall we would expect it to be negative. Any questions on that? Okay. So coming over here, looking at this coordination compound, again, as we just talked about a second ago, this will be our complex ion part. This will then be our counter ion part. So that's our complex ion. That is our counter ion. Again, just from the positioning of each of these things, we should already know that overall our complex ion is positive and our counter ion is negative in this case. So let's go make sure we know that for sure. So first off, let's take a look at NH3. NH3 is ammonia, not ammonium, but it's actually ammonia, which means it actually has no charge, right? So all 6 of those have no charge. Our nitrate, which is NO3, is -1, and there's 3 of them, which gives you a grand total of -3. That means in this case, our chromium should be +3. So the chromium here would have an oxidation state of +3. Any questions on that? So what does that mean for our complex ion part? Well, we've already determined at the beginning there that we know it should be positive. And to verify that it is positive, if we just take our complex ion part out by itself, this again being 0, this being +3 as we just determined, means that overall my complex ion here has a +3 charge. And that makes a lot of sense when we look at our counter ion over here. And our counter ion is nitrate, which is NO3 minus, but not just one nitrate to balance out the charge. We need 3 of them to balance out the charge. That gives us a -3 to balance out our +3 charge here. And again, when we put all that back together, that is how we get to this crazy looking formula here of our coordination compound. Again, we need those 3 nitrates to generate a -3 charge to balance out the +3 charge for our complex ion. Question on that? So in this case, this is also a very good example of, as we see here, our complex ion is positive and our counter ion is negative. So this is a very good example that demonstrates what we were talking about just a minute ago, that, your complex ion can be positive or negative, and just like that, your counter ion could also either be positive or negative. So, you can have it either way there. Any questions so far here? So let's then talk about what is the coordination number for each of these guys in the complex ion. So what would the coordination numbers be here for our first guy and our second guy? So take a second here, a minute or two, or a few seconds, and think about each of those and think about what the coordination number for each of those should be. And if we look at this, the complex ion part is obviously just a part in parentheses brackets. And in this case, this is our ligand. And our ligand in this case is hydroxide here, which, looks something like this. And that is a monodentate ligand, which means the coordination number here would be 4 because there's 4 of them. When we come over here, the ligand again, and the guy in the brackets is going to be our NH3, which again, as we saw on that chart, and I drew a number of times, NH3 also going to be monodentate, and there's 6 of them here, which means the coordination number here would be 6. Any questions on how to figure out what's the complex ion, what's the counter ion, the oxidation number, or coordination number? Now that we can kind of dissect the whole thing in terms of our coordination compounds, let's now talk about how we go about naming these guys. So there is a little bit of nomenclature happening here. It's kind of some weird nomenclature happening here. But let's talk about some of these rules that we follow. The first one is, again, sort of in relationship to our ionic compound sort of thinking. Again, the cation is named first, followed by the anion. So just like in a normal kind of situation, we're going to go positive, followed by negative. And within a complex ion, we name the ligands first in alphabetical order, and the metal atom is always named last. So what that means is, if we're naming a coordination compound, which is, again, like we just saw there, you know, some guy in brackets, and then your counter ion perhaps on either side. When we're dealing with just the core complex ion part of the name there, we want to put all of the ligands in alphabetical order, regardless of disregarding prefix, actually. And then we want to name the metal last. When we have ones that ligands that are negatively charged, it ends with letters O. Some neutral ligands are usually called by the name of the molecule. There are some exceptions, like water is aqua. Some books even call it aqua with an A. CO is carbonyl, NH3 is amine. If we end up having several ligands in the same molecule present, we do use some prefixes for that. So we use things like di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. Now, the fun thing is, if you actually have a ligand that already has a prefix in it, then you will actually go to some different sort of prefixes. And we would use things like bis, which means 2, tris, which means 3, tetrakis, which means 4, to indicate how many that we have in there. So what do I mean by that? Well, what I mean by that is, if you think about the ligand that we talked about, which is En, if you spell out that ligand's name, that is Ethylenedyldiamine. So because the actual ligand itself has a prefix in it, and it is this guy right here, this di, if we had 2 of them, we would not use di for the name. We would then need to go to bis in this case. So that's probably, I would say, maybe the common one that you'll come across is that ethylenedyldiamine. I will also see that sometimes for oxalate, the C2O42 minus, even though oxalate doesn't seem to have per se a prefix in the name, sometimes people will also, for oxalate, kind of use these prefixes as well for that. So those two there, those sort of bidentate sort of ligands will sort of sometimes get those prefixes. Now, we always include the oxidation number of the metal in Roman numerals. So when we name these sort of coordinated compounds or complex ions, they are really treated kind of like type 2 ionic compounds, where you use Roman numerals, again, because, you know, they are transition metals, most of them. So we do use Roman numerals with them. We also use Roman numerals with some of these metals that we normally do not do in sort of normal nomenclature. So for example, silver, right? Silver is always +1, and we don't usually do the Roman numeral 1 when we write out silver chloride or silver nitrate or any of those type of things. When we do deal with something like silver in a complex ion, we actually do use the Roman numeral, and we use the Roman numeral 1 there as well. So some of these guys where, you know, zinc, for example, as well, where we don't typically normally in nomenclature sort of use the Roman numerals, here in this sort of application, it is common to use the Roman numerals for those guys. We will even see some things, as odd as it may sound, that the metal has like a 0 oxidation number. So we'd use 0 sometimes in there as well, where the Roman numeral would go. So as odd as it sounds, it can happen. And, you know, we sort of display that with even writing a 0 in place of the Roman numeral. Any questions on that there? Now, the one last one on the bottom there that, you know, sometimes gets people is, if the complex ion is negatively charged, or it's an anion, then we actually will use sort of the old school name, if you will, for metals. So what I mean by that is we'll use the ones with the ATE. So instead of iron, we'll use something like ferrate. Instead of copper, we'll use something like cuprate, kind of those historical or origin type names. You know, argentate for silver, stannate for tin. So we'll use those sort of old school type names with the ATE. And that's when a situation occurs that your complex ion is actually negatively charged. So in like that previous example we were looking at, where'd that guy go? In this case, our complex ion was negatively charged. So when we would get to the part of naming gold here, we would use arurate instead of gold. So we'd use something like arurate instead of gold. Here our complex ion is positively charged. So when we would get to the part of naming the metal here, it would just be chromium, just like you would find on the periodic table. So again, that's why it's important to be able to recognize whether or not your complex ion is positive or negative when we go about sort of naming these guys. Any questions on that there? So here's a table of some of these ligands and some of the names that are sometimes used. So we have aqua, and again, some books will call it aquo for water, amine there for NH3, methylamine for our CH3, NH2, some carbonyl. And then our sort of halogens are named kind of very much like they're named in organic chemistry. We have fluoral for fluorine, chloral, bromol, iodo for iodine. Hydroxide is hydroxo, cyanide is cyano. So these are some of the names that we use for these ligands. Here's some of those older school sort of names like ferrate, cuprate, plumate for lead, argentate, arurate, and stannate. And here's some of these other ones, some other favorite ones that pop up along the way. We have our good carbonate, which is like a carbonato, in case you're ordering that at Starbucks. A nitrite is a nitro. Our oxalate is an oxalato as well, in case you don't want a carbonato when you're ordering that. Ammonia is an amine. Here's our ethylenedyldiamine. It's ethylenedyldiamine. Again, this is the one that's really sort of abbreviated with the EN. This is our EDTA in terms of what's going on there. So why don't we take a second here and give you an opportunity to try a couple of those guys we were just seeing the other slide. Why don't you take a moment or two and see if you could come up with the proper name for this guy that we just saw, and also the proper name for the other guy that we just saw. All right, so take a moment and see what you come up with, and then we'll go over these guys here together. These were the two examples we just did about oxidation numbers. See if you come up with the name, and then we'll see if we're all on the same page. Okay, so let's go through these again to kind of show you what you should kind of be doing and looking at. We'll start with our first one here. And since we previously did some of the work here, we already figured out that our gold here is +3. Obviously, you'd probably want to figure that out if you have not. We also done some of the work, and we could just see from the formula that this is our counter ion. This would be our complex ion. So this would be a case, as we also saw earlier, that our complex ion is negative. So first off, what that means is we're going to kind of roll old school there with the name for gold. So again, that's going to be arurate instead of gold. We already know is 3, so that's going to be arurate 3 here. We also have 4 hydroxides. Again, hydroxides no longer sort of called hydroxides here, going to call it hydroxo. And since there's 4 of them, the prefix for 4 is tetra hydroxo. Now we just kind of need to put it together here. So we start with our counter ion in this case, and our counter ion is potassium. So just like if you had like K2O, you would call this potassium oxide. It doesn't matter how many counter ions there are, you would just call it what the name is. Same idea here. This is going to just be potassium for our counter ion. Ligands coming first. So since we only have one, this is going to be tetrahydroxo. Metal in the complex ion comes at the end of the complex ion name. Arurate 3. Made a big piece of paper for this one, yeah. So that is potassium tetrahydroxo arurate 3. Any questions on that name? Okay. Now looking at our second one here, we see sort of the opposite like we did before. We did, again, some of the work here. We already know that's +3. We already know this guy is positive, which is our complex ion. We already know that this guy here is our counter ion. Now, because it is positive, that means we just use the regular name there. Also going to use a Roman numeral 3 to indicate the charge. We have, in terms of ligand, 6, which is hexa, and NH3, which is amine, which is right there. So we have hexaamine. And at this point, we have our counter ion here, not complex ion, our counter ion, which is nitrate. And even though you have 3 of them, it would just still be called nitrate. So very similar to if you had something like this. This would be iron Roman numeral 3 nitrate, even though there's 3 of them, right? It has no effect on the name. Same idea here, will have no effect on the name. So for the most part, your counter ions are pretty much just the name of the counter ion is what you do. If it comes in front, it's probably going to be a positive metal. So you just use the name of the metal. If it comes on the back end, you would just name it like you would an ionic compound, again, regardless of how many there are. So putting this together, again, starting with the ligand, this would be hexaamine, chromium 3 nitrate. Any questions on either of those names? Okay, so why don't you try some here? Why don't you give this guy a go, and why not? It's a hydrate. Let's see what you come up with. That there's that dot on the bottom shouldn't be there. So it should be K3 CrC2O4 and hydrates, if you remember, have the little dot 3H2O. So this is a coordination compound that's also a hydrate. All right, take a moment here and see what you come up with on this name. This with you and see what we got going on here. So we got a couple of things going on. We're just going to leave the hydrate part here. Well, we take care of it right now if you want. So as you know, you basically name it hydrate and how many waters there are. So there's 3. So that would be trihydrate. This is our front part here. This is our complex ion. This is our potassium, which is our counter ion here. We know that our complex ion is negative, which means we're going to use sort of the old name there for chromium. Let's first figure out what is the charge there, oxidation state of chromium. So starting with this C2O4, that's oxalate, which is -2. That's a -6 overall. There is +1 for our potassium on the outside, and there's 3 of them. So that means that the chromium here would have an oxidation number there of 3. That also means that in terms of our complex ion part, that would be chromate, ATE, right? And Roman numeral 3. Any questions on that? We have 3 of our oxalate, and oxalate is oxalato, and that's our oxalate. Now, this is one of those ones I mentioned earlier. That's a, even though you don't really see a prefix per se in here, sometimes people will do tris oxalato here because it is 3 of them, and Maybe historically they've done it. You could also do trioxalato here, would be okay in this case. Try for R3. So we got that part of it. We're going to now start with our first part, counter ion. Even though there's 3 of them, it is still potassium. Again, just like we were talking about with K2O, still potassium oxide. This would be potassium. Here we're going to go with either trioxalato, chromate 3, and since we do have the water there, trihydrate. That is a name of names right there. There it is. Again, very commonly, you will sort of see people without oxalato go with the tris oxalato and chromate, Roman numeral 3, trihydrate as well. Any questions on that name there? Most of the time, you probably won't have a hydrate involved, but you kind of name it the same way. Lastly, let's talk about coordination number here. Take a second and think what the coordination number here should be. All right, so this is our ligand right there. That's oxalate. There's 3 of them. So the coordination number here is going to be 6 in this case. So a reminder that oxalate is that one we were looking at previously. It binds in 2 places, as is bidentate, per molecule. So since there's 3 of them, that would give us a coordination number here of 6. Any questions on that there? All right, let's try a couple more here. Let's try both of this. So top one, we want name. Bottom one, we want proper formula. So see what you come up with. And we'll talk about it here in just a sec. So taking a look at the first one here, we see again our complex ion part is positive. As it comes first, this would be our counter ion, which is negative. So again, what that means is we will go with the irregular name there for our CR, which is chromium. We should figure out what the charge is or oxidation state. Water is 0. Cl here is -1. There's 2 of them, gives you a -2. On the outside, we have another Cl, which is also -1. So again, to get us to 0, we would have a +3 charge here on our chromium. So we have chromium, Roman numeral 3 happening. We also have 4 waters. Prefix for 4 is tetra, and water is aqua, whichever one you like. And we also have 2 of the Cls. 2 is di and chloral. And then we have our counter ion, which is our Cl as well. So putting this together in alphabetical order would go with tetra, aqua, dichloral, chromium, Roman numeral 3, and then our counter ion is named just like normal, which would be chloride. Any questions on that name? Now it is alphabetical order regardless of prefix, so we're looking at A versus C here, and that is why obviously T comes after D, but we're actually looking at the A versus the C here in alphabetical order in terms of our prefixes. Question on that one there. What would be our coordination number here? Our coordination number here would be 6 in this case. We have 4 waters. Each one is monodentate, so that's a coordination number 4. And there's also 2 chlorides attached directly to the metal, which gets us to 6 in terms of our coordination number. Any questions on that there? Now, what would happen if we didn't have our counter ion present and we just had this guy given to us? Well, we already know this is a positively charged ion, right? And we already know that this guy is +3. This is -1. There's two of them. That is a +1 overall. So if we had just this ion given to us, this complex ion, and we wanted to name it, what would we call it? Well, we would call it pretty much what we have above. This would still be tetra aquo dichloral chromium Roman numeral 3. And since we don't have the counter ion, we would call it an ion because it does have a charge. So basically you would name just the complex ion by itself the same way, just leave off the counter ion in terms of the name. Any questions on that there? All right, looking at this one here, we're actually going backwards in terms of we have the name and we just need to kind of put it together. So really we just kind of want to think about the parts here. Well, this is the complex ion part for sure. And I know that because when I name a complex ion, the metal always comes at the end of the complex ion name, not the actual name of the coordination compound, but actually the complex ion part of the name. And since I see cobalt 2 there, that tells me that is my complex ion. That tells me this guy here is my counter ion. So what that means is, let's just take the parts. So we know sulfate is SO4 2 minus. Tris ethylenedyldiamine. Tris means 3. This is our En. So again, if you don't want to write out the formula, you can use that. If you really want to write out the formula, you can do this as well, if you like. So most people will probably go with this guy. Cobalt Roman numeral 2 means I have one of those guys. So now we just kind of need to put it together. So we'll start with our complex ion part, which comes first. So we'll take our cobalt. We have our En, which is 3. And now it's important to think about what is the charge of just the complex ion part. So since this guy is neutral and the cobalt has a +2 charge, that means that technically speaking, our complex ion is +2. Why is that important? That is important because our counter ion here has a -2 charge. So that tells us that we actually just need one counter ion here to balance out everything. And that would get us to a formula that looks like something like this here. Any questions on that one there? Coordination number here would also be 6 in this case. Again, because this is bidentate and there's 3 of them, 3 times 2 would be 6. Questions on naming, formulas, any of that type of stuff here?
Professor?
Yeah.
Is the total of the complex ion and its counter ion ever comes up other than 0, or is it always 0?
It should always kind of usually be 0 in, I think, all cases. And that's the idea of sort of the coordination compound. Because you have that counter ion, the idea of it is like an ionic compound to kind of balance out the charge. So the counter ion should always sort of balance out the charge of the complex ion part. So coordination compound, where you have both of those things, the complex ion and the counter ion, should always equal 0. If you have just the complex ion by itself, obviously it could be either positive or negative, and you would have more of this situation in this case. But yeah, so the coordination compound should always end up being 0.
Thank you.
Welcome. Other questions on that? Okay, so
Oh,
yeah, I'm sorry, go ahead.
sorry. So for the coordination number, did you get that from the EN3?
I did because
Okay.
the coordination number basically is based off of the complex ion part. It's a part where you have the metal and all the ligands basically attached to it. And in this particular case, it basically means what we have is We have a cobalt in the center, and we have 3 of these guys around. Let's draw one this way. Go this way. And basically, the first guy is going to attach 1 there and 1 there for coordination number 2. Second guy will come in also with those 2 nitrogens for 4. Third guy will come in with the other 2, which will get you to 6. So that's where the coordination number 6 comes into play, because really EN is a bidentate, which means you kind of get 2 for 1. So 2 sort of binding for every 1 molecule.
Okay, thank you so much.
Yep, you're welcome. Other questions on that? You will need to know the common ligands and stuff on those tables, the names, and this like table here, how to kind of go old school name with the metals as well. So you'll need to know those. Yeah. They won't be provided for you. Other questions?